Okay, we're going to start with the last of the talks, and then after which we'll have the panel. And this is Mehtaab Sawhney, who's here at Columbia, but also currently at OpenAI, and he's going to be speaking about LLMs as research assistants.
Yeah, so thanks, Ivan, and thanks for the invitation. So what I'll be discussing is LLMs as research assistants, and I think in my abstract, I'm currently at OpenAI, sort of thinking about using sort of helping improve the state of affairs of AI and math. But I think what I wanted to focus on for this talk was something a little bit more concrete, which is just sort of what. When I do mathematics, I found in recent times I was using the LLMs more and more, and sort of how I'm thinking about that. So yeah, so over the last year, I think it's fair to say that LLMs have sort of become vastly more useful for research and research adjacent tasks. When I say research adjacent tasks, I don't mean like proving the main theorem in a paper, but I mean occasionally you need to find something in the literature, or you're trying to figure out if the problem you're having is closely related to things you've seen before. So that's what I mean by a research adjacent task. And this talk is really going to be a series of stories. I'm not going to sort of discuss any benchmarks or anything like this. Instead, what I'm going to try to discuss is sort of where they're effective and sort of maybe point out some limitations that the model sometimes have. So I think it's useful sort of to ground ourselves to sort of see what like a frontier example looks like. Sort of what are the most, maybe the most difficult problems which a model has sort of resolved kind of just by itself. So this is an example that comes from a paper released by OpenAI a few months ago, but I was not involved in this particular example. So there's a problem about random trees that came from the Conference on Learning Theory. It's an open problem from about 2015. So the problem is as follows. It's not so important you catch all the details, but just a sense is important. So you start off with a fixed vertex, and it's given weight randomly W or 1. So W you should think of as some real parameter bigger than 1. And what you do is at every time step, you define the attractiveness of a vertex to be the sum of the weights of its nearest neighbors. So at time step t, a vertex vt arrives, and it sort of attaches to the other one of the other t minus 1 vertices with weight, and it's not attached uniformly at random. Instead, you attach with probability proportional to the attractiveness of the given vertex. And this new vertex, it attaches, and then it's randomly assigned a weight W or 1. So the question is, I give you a snapshot of this t, it's some large time t, can you estimate W accurately? So in particular, one thing to note is that you're not actually given the labels W or 1, and in particular, you're not told the value W. You're just given this tree structure, and you want to estimate W. So this is a perfectly natural problem. It's sort of, I think there are many different forms of random growing trees, and this is sort of one example. I think an example which is fair to say sort of hadn't been looked up by that many experts, but okay, it's a perfectly natural mathematical question. And so if you give this to GPT-5 Pro, it won't solve it, but if you develop a sort of bespoke harness that's internal at OpenAI, it can solve this problem end to end. You just give it the problem, and it outputs a complete solution. And what I mean by gives a complete solution is, so there are two things the model has to do here. First, it has to give you a statistic, which sort of tells you how are you going to estimate W, and B, it has to prove it's correct. So the key statistic here isn't super tricky. It's somehow the fraction of leaves in the tree, so it's pretty natural. But actually proving that this works it's finicky. So the model at least needs to understand something like what's called the differential equations method, and you need to find some sufficient statistic to understand the tree. So I think this is about the level of where frontier systems are. It can solve an open problem. This is a genuine open problem, but it's relatively modest in scope. And sort of there's been, I think if you look on Twitter, there's been a lot of discussion about such AI systems solving autonomous problems, mostly on the Erdish Problems website. And I think it's fair to say that many of these have also been modest in scope. But that's where we are right now. But I think one thing which I want to emphasize is that sort of things change pretty rapidly. And so the second example, I think, is something that came from my own work. And I think was sort of, it had a real impact on me. So So I was working with Ben Green on a very simple problem. So it's what's called the multiplication table problem. So you have an so the n by n multiplication table is just, so in school you learn the 10 by 10 multiplication table and you write it as like a grid. And you can obviously generalize this to n by n. And the question we considered is sort of how many distinct integers are there. So we weren't the first people to think about this. Erdős originally asked about it. There was substantial work by Tannenbaum, and then Ford determined this up to a multiplicative constant. And in work with Ben, we sort of determined it exactly. But so it turns out the answer, this is a difficult problem, and determining what Mn is tricky. But part of the answer involves a certain real valued function, which is all we're going to discuss for the rest of this example. So let's define the function g of x, which is the sum over z over a parameter over an integer z in the integers of log 2 to the x plus z times 1 minus e to the minus 2 plus z. So there's just a couple things I should note about this function. So first, it's one periodic. So if you shift z x by 1, you're just sort of shifting the sum. So this is a one periodic function. And okay, you can graph this function and something pretty amazing happens. So if you graph the function, you get some kind of weird numerical property. So let little m be the minimum of this function and capital M be the maximum. And if you work it out, it's like 5 to 6 decimal places, if I remember correctly. Like it's either 6 or 7 decimal places. So the maximum and the minimum differ by some extremely small amount. So it's something like 1 plus 2 times 10 to the minus 7. So what I've done here is I sort of plotted the function, normalizing it so that it lives between 0 and 1. But in reality, if you like plot this, it's flat to the I. And so, okay, so how did we discover this? Well, we were in the process of writing paper, actually still in the process of writing this paper. But okay, I plugged it into GPT and sort of asked it to produce a numerical plot. And okay, it told me this fact. Okay, but I mean, this is somewhat unsatisfactory. If you look at this formula, it's not obvious that this is true. So then what I did was I asked GPT to prove it. And I asked this actually several months ago. So I went through my emails. I was looking at this in July of 2025. And so the models at the time, so this was something like GPT-04 mini. And you should think, so okay, so the main corollary you get about this function g is that the max of it divided by the minimum is something like 1 plus 2 times 10 to the minus 7. So, okay, so it's always greater than 1 for any function g, but okay, it's really, really close to 12. So okay, when you did this originally, I checked through my emails sometime in July, and when you ask GPT, it sort of points out that probably this is some kind this is probably some function of the fact that you're summing a smooth function along integer shifts. And that suggests that you should try to apply the Poisson summation formula and sort of understand how the Fourier coefficients decay. So this is pretty natural. There's several examples of this in the literature, and GPT goes like quite far. It sort of does the calculation and it writes down a Fourier series. When I did it in July, it made a few mistakes, but it was like very, very close. And I think if you prompt it once more, sort of tell it look up a table to do the calculation correctly, it does it correctly. So it couldn't do it autonomously, but it got quite close. And I mean, when we first saw this, I think it was unclear to us whether this was a function of g or just some like more abstract fact. It turns out this will hold for almost any function which is sufficiently nice in some sense. But okay, so this was in July. I think if you asked it in, say, October of last year, when something like GPT-5 Pro appeared, you can actually just give it to it, and it will give you the correct Poisson summation formula. So this is a formula g of x. As far as I know, it's not in the literature, but closely related things are. And then you want to know, can you prove this bound 1 plus 2 times 10 to the minus 7? And what you need to do is you need to understand how the gamma function decays along vertical lines. I'm sure this is in the literature, but if you ask it for proof, if you ask GPT-5 for a proof, it gives you a very simple contour integration argument, which is sufficient to sort of derive this bound. And just to make sure I'm not lying, this is sort of the example. I pulled this from my old conversations with GPT. So yeah, I think I just asked it to plot the function and then asked it for proof of it. So I mean, this will be a lemma in a forthcoming paper. So okay, this is essentially GPT handling some rather minor, but okay, pretty lemma in the paper. But I think one thing that sort of is true about both of these examples is they're not typical of my current day-to-day interactions with GPT. So in the first example, we just handled the whole problem and we got a solution back. And in the second example, sort of a very self-contained lemma, and you got a proof back. Most of the time when I'm doing research, I'm not in the state where I have a clean self-contained lemma, which I sort of roughly know what I want to prove, or have quite an exact understanding of what I want to prove. And I think that's the dominant state as a mathematician. So I think it's also important to discuss how you use the tools outside of those cases. And so so I think the important thing to say is that for me, most of my interactions with LLM are much more dynamic. So there are many more interactions of back and forth, and I try to make it narrower than prove my lemma. I think that's just a current. That's where we are currently, but I think, I mean, obviously these models are changing quite fast, so that's important to keep in mind. Another piece of advice, which I think I learned the hard way, is that models perform best when the task is well scoped, and sort of what you want both as input and output from the model should be made explicit. So you give it a task and you say, what would a successful outcome be? Additionally, if you're giving additional context, you don't want to sort of confuse the model. If you give precise additional context, that's often quite valuable. I think a very useful example, so reference in this direction, is there's a paper on arXiv. Maybe the arXiv ID won't, but if you just search sort of prompting public models to get a gold on the IMO, this comes up, and it discusses. There's a group of researchers which, sort of by very clever prompt engineering, are able. At the time, I think it was Gemini 2.5 Pro and whatever OpenAI's leading model was at the moment, and they used it and they were able to sort of get the publicly available models to solve 5 problems on the IMO. That statement should be slightly qualified, and the qualifications are carefully written in the paper. But I think it sort of shows that I think if you just feed the statement of the IMO problems, if you had fed just the statement of the IMO problems into the model at that point, you wouldn't have gotten a. But by sort of explaining really quite carefully what you want the model to do, you could get substantially more performance out of the models, which is a kind of strange thing when you initially see it. Okay, so I'll now discuss sort of maybe 2 more typical examples which came up in my research. So one is actually from a forthcoming paper with undergraduate student, Brandon Letwin at the University of Alberta. So I'll discuss the question, what came up, and then sort of how you use it. So we're considering a question raised by Salem and Zygmunt in the 50s. So what you do is you look at the following polynomial. You sum from I equals 1 to n of epsilon I x to the I. So this is just a random polynomial with coefficients of plus minus 1. And so we sort of want some kind of control on how bounded this polynomial could be. So I'm going to look at the maximum of this polynomial fn of x between -1 and 1, and I sort of want to have a lower bound for this quantity, which holds uniformly in n. So at this point, this seems like sort of a standard question, slightly non-standard, but of the flavor of question one considers in random polynomials. So it turns out what it turns out is when you study this problem, all that really matters is the behavior very close to 1 and -1. And if you do sort of relatively standard things, apply the KMT theorem, what this reduces to is understanding the following question about Brownian motion. So I have a Brownian motion between 0 and 1, and I integrate it against e to minus xt between 0 and 1. And so there's a parameter x here, and then I take the supremum over all x bigger than 1. So I want this supremum to be less than epsilon. So if just by looking at this is some Gaussian process. relatively complicated Gaussian process indexed by the parameter x, and I want to understand what's the probability between minus epsilon and epsilon. Now, when I saw this, it seemed like something which should have been relatively standard, but I think if you ask the statement of this problem and you plug it into a search engine, it's very difficult to get a solution out. I think I tried for a bit, I couldn't get anywhere. But sort of what I do now, instead of using a search engine, when I get some kind of well-posed problem, which I suspect is somewhere in the literature, I just ask it to GPT. I think I literally asked, look at the, I sort of defined this this Gaussian process and asked what the small ball probability that lies between minus epsilon and epsilon is. And if you do this, then GPT 5.2 thinking just locates the correct reference. So it tells you that this probability is at least somewhat well understood. The log probability of this happening is like minus log 1 over epsilon cubed. And so, okay, we turns out, I mean, so this was somewhere in intermediate state. Actually, in our work, we refined this, but okay, at some point, this is sort of a crucial intermediate state. So if you're looking for so I think one way of thinking about this is instead of trying to search by keywords like you do with Google, you can sort of search at a more contextual level. And that's been something I found to be incredibly useful. And maybe the last thing I want to discuss is sort of perseverance with the models. So this is an example that comes from a recent paper I had on random matrix theory with Matt Kwan, Zach Hunter, and Lisa Sauerman. And in this case, the proof of the lemma was found by the humans, but because of some interactions, I sort of wanted to see could the model prove it? And this is not the hard part of the paper, but it's a somewhat non-standard lemma, and I think it's good to think about. So the lemma is as follows. So let A1 through AK be subsets of R mod Z, and you have that each of these sets AI, they only take up at most half the torus. Now, so okay, I consider these K sets and I consider the product set, and I have a set inside the subset A1 dot 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 AK. So S is a subset living in the torus to the power K. And what I wanted to prove was that the volume of S plus S is bigger than 2 to the K times volume of S. So maybe let me give some context about this and then I'll explain what happened. So, okay. So there's sort of a special model case, which is the motivation for the statement. So you can sort of naturally parameterize the circle with the open interval between -1/2 and 1/2. So the most natural set of volume at half is like the middle half interval. So suppose you have a set S, we'll consider in 2D, which is between -1/4 and 1/4, -1/4 cross itself. So I have a set S inside this like smaller subsquare. And if S is a convex set, then S plus S equals 2S. So sort of because you're inside this smaller square, S plus S sort of can't have the effects of wraparound. And so addition in this case, sort of it looks exactly like addition in R. And then the fact that S plus S has at least volume 2 to the dimension times the volume of S, that's a well-known consequence of the Brodmann-Minkowski inequality. So this sort of explains where this restriction of A1 and cross A2 comes from. On the other hand, there's sort of a case where this fails. You could have S, which is actually very small volume, but it's sort of essentially a one-dimensional strip. And when it's a one-dimensional strip and you sort of look at S plus S, then you sort of only expand by 2. This is really because the set S, you shouldn't think of it as two-dimensional, the torus. It's really secretly a one-dimensional set across the full interval. So that's why that sort of explains where the condition is coming from. So this is not the first lemma we thought of. There's some other lemma which we initially had. We had some very ugly proof, which is quite complicated. Eventually, one of the authors suggested maybe the stronger statement was true. And while we were interacting with when this process was happening, I was sort of by habit, whenever I had a statement, I would just plug it into GPT and sort of see, can it do it for me? And it kept giving giving slightly wrong proofs, but it kept suggesting the technique of compressions. And it turns out as soon as the statement was said, very quickly, essentially all of the authors simultaneously realized compressions very quickly solves this problem. So because GPT had kept saying the word compressions to me, I thought, okay, maybe this is an interesting case of sort of, can the model prove this lemma? And so, okay, I tried this 5 times. The first 4 times it gave wrong proofs, which are quite subtle to check. And honestly, I probably would have given up quite a bit earlier, except I could sort of look at the proof and check, does it apply equally well to the second example where I haven't sort of used all the hypotheses. So, okay, it would. And yeah, but eventually, okay, because I could sort of quickly check whether the attempts were wrong or not, I kept trying, and okay, on the 5th attempt, GPT sort of gave a proof, and it's like syntactically equivalent to the human proof. Sort of once you know to use compression, there aren't so many things to do. And I think that sort of gives a model of how, if you sort of work back and forth with the models, they are quite a bit more capable than if you just sort of try to use them in one shot. I think actually a really good example of this is the Erdős Problems website. So now there have been a number of solutions obtained to modest problems, to be clear, but where individuals sort of go back and forth with the model maybe 10 or 15 times and just try to get the model to refine its approach. And I think the thing that's useful is that so many of the people who are doing this have sort of released their prompts, and you can see they're not sort of giving mathematical hints, but okay, they might say, I like this part of your suggestion model or that part, or they're sort of just guiding the model along, pointing out errors. But I think they're able to get much more out of the model this way, and often the model is suggesting what is the key idea in one of these solutions. And that's sort of much more capability than if you just use the model in one shot. I think that degree of persistence, I think, is incredibly important using the models. Yeah, and that's all I had to say. So, thank you.